talked about a number of different bells and whistles. So the idea here is not that you are experts in multi-level item response theory, or that you're experts in the translation between the multi-level formulation and the kind of classic multivariate formulation, but that you're aware of this really cool coincidence, this really cool intersection. It's not a coincidence at all, but a really cool intersection or overlap between item response theory or psychometrics and multi-level models or mixed effects models. So when we come back to our first question, if we load the data and we look at the data, what we see is that we have a multivariate Y representation. In other words, each row represents a person, and each column represents an item. So each kind of row by column cell represents an individual persons to a particular item. So that's kind of the classic representation in IRT. So we decided to change that. We decided to make it into a long format, and when we do that, what we have is a univariate long where we have items that are nested within people. So now each row does not represent a person. Each row represents a person's response to a particular item. And so we will have the same person represented multiple times, and then that person, so those items are kind of nested within a person. It's a type of repeated measure or multi-level designs where you have multiple measurements on the same person. In this case, the multiple measurements are just the items that they responded to. So when we estimate that model, is there any questions about the code that we have here that was posted? Everyone feel somewhat comfortable with that? It'll be a lot more comfortable if you take multi-level models and if the multi-level class is taught in R, which I think it will be in the spring. If you ask for a summary of that, you get the following. So let's start somewhere right about here, and we'll go down. And if there's a particular parameter that you're interested in me interpreting and I skip it, let me know. So the first one is the person variance. This is the variance of the latent trait. In this case, I guess it's the propensity to communicate, propensity of the management to communicate to employees. And so if you look at the variance among individuals, we see that the variance is roughly 0.56. This is a Roche model, so the way that that's identified, the way that we're able to estimate the variance among people rather than fix it, is because we fix the loadings of each one of the items to be 1. So in a Roche model, you can either choose to fix the loadings to be 1 and estimate the variance, or you can fix the variance to 1 and estimate the loadings. If you fix the variance to 1 and estimate the loadings, that's the 1 parameter version. It's a type of Roche model, I guess, or maybe a Roche model is a type of 1 parameter model. So you either have to fix the loadings or the variance. You don't have to do both, as we've discussed, to identify the model. So in this case, we're able to estimate the variance, and so we're able to identify or estimate the ability of our model or these items to discriminate among people in some ways, or to differentiate, not discriminate in the kind of the loading parameter sense, but to differentiate in terms of what is the kind of propensity of different individuals, or the propensity that is reported by different individuals of management to communicate with their employees. And so in this case, the variance is about 0.5, and that's a pretty healthy variance. When you get concerned is when you start to have variances that approach 0. Things that are really small, like 0.1, doesn't mean that it's not doesn't necessarily mean that it's bad, but the smaller the variance, the worse your model's doing, so to speak, in terms of differentiating among people on the latent trait. And that's really the kind of one of the principal goals that you have when you're measuring a latent trait. If, for example, you only had 3 items, and those 3 items were really poor, you would typically have a variance that was pretty small, especially if you had a 2-parameter model where you did not fix the loadings to be 1 or not. So in that situation, you're getting very little information from those items. I don't like this this model. I like the other version better. We didn't write it though. If you write the model as something like So if you reparameterize the model so that you suppress an intercept with this -1+ command, this gives you the actual item difficulties or easiness parameters for each one of the items, as opposed to using the alternative one where you have an intercept. The intercept represents the difficulty or the easiness for item 1, and then item 2 would be the difficulty or easiness would be the combination or the sum of item 1's easiness plus item 2's easiness. So in this example, we have the first item, the difficulty. These are all represent the difficulties, because difficulty is another way to say them is intercepts, so to speak. So this one, this is actually easiness. If we wanted to parameterize in terms of difficulty, it would be negative this. Remember our key interpretation, or the kind of classic interpretation says something like theta minus the ability, the latent trait, minus the difficulties. But in this package, we would have something like theta plus b, because it's your typical regression formulation. So b now represents the easiness parameter in this package, whereas alternatively in the LTM package or other packages, sometimes it's represented as the difficulty parameter. Classically, it's been called the difficulty parameter. So the difficulty of item 1 is 0.58, or you could say the easiness of item 1 is 0.58. The difficulty of item 2 is negative 0.38, or the easiness is positive 0.38. You can go on and say that for each one of the items. Is there a question, a specific question? An interpretation of any of these? Yes?
Kelsey, so would you please explain the -1 plus variable, you suppress the intercepts again? Why we?
So this is just R's notation for suppressing an intercept. So if you don't want an intercept, it automatically includes an intercept in regression models, including in mixed effect models. But if you don't want that intercept, you can just suppress it. So it's kind of like saying when you have, if you've heard about dummy variables or dummy effects, dummy coding, you usually need one less than the number of groups. So if you have a simple binary categorical variable like true or false, you only need one dummy indicator to indicate true. If you have a 5 category, in other words, what's your favorite beverage? Coffee, soda, juice, water. If you have 5 categories, you only need 4 dummy variables. And that's because you already have a variable that's capturing that 5th category, and that's usually subsumed by the intercept. And so if you want, you could have 5 dummy variables, you just kill the intercept, or you just remove an intercept, and then you would estimate the specific intercept for each category. Does that make sense?
I understand the dummy variable part. So how integrated with this coding? So we use a -1 want to.
Well, this is just a dummy. This variable, the variable is just a categorical code, right? If you look back at our data set, the column that's called variable, it just says item 1, and then it'll say item 2, 3, 4, 5, 6. It's just a categorical code. It's just a dummy. So all we're doing is when we include this in the model using this right here, this is a dummy variable. R interpreted, because this is a categorical variable, and R automatically creates a dummy variable in the background, and so it automatically has your simple dummy coding variable pattern, and it creates. We have 6 items, so it would create 5. If you had an intercept, it would create 5 categorical indicators for whether it was item 1, item 2, item 3, item 4, or 5. But when you suppress this, it'll create 6 categorical indicators, 6 dummy variables.
So when you're fixing the loadings in this, where is that in your R code? How do you tell R that's what you're doing, that you're fixing your loadings to 1 to identify your model?
So it's implicit here because GLMER, generalized linear mixed effects models in R, is it's generalized linear model, so it doesn't do the 2-parameter version.
Okay.
So in order to get a 2-parameter version, you need a generalized nonlinear mixed effect model. It's nonlinear because you have that discrimination parameter multiplying the theta and the b parameters.
So it's just a given when you're using that.
Yeah. So it'll only run the Roche model in this approach.
Okay. Thanks.
Other questions?
I'll ask a broader question. So the underlying assumption
conceptually it's straightforward. What you would do in your simple, the coding is a little bit intense. You have to create some kind of really interesting design matrix to indicate which patterns you're talking about specifically, but you can do it. And basically, conceptually, you would just have another variable called dimension. As a dimension 1 or dimension 2. So you would just create the loading patterns that we typically have seen in all of our other analyses. Yeah. So you could easily do, a multi-level, 2-dimensional Rashomon or something of that nature.
Sounds terrifying.
Yeah, well, it's not. I mean, the coding is a little bit messy, but you've done it, right? We've talked about multi-level item response models, and you've done I'm pretty sure we've done a few, like multi-level bifactor models or multi-dimensional models.
That's the problem. When we do with you, it's super easy. But when we are doing it by ourselves, it's not that easy.
Yeah. I recognize that. It's why these things require time and effort. They're not. There's only so much we can cover in a class, so it's kind of introducing some of these concepts. And at times it feels very superficial, but the truth is, if we talked about one single model for the entire semester, you would have it down really well, but then you probably wouldn't know that multi-level models had some intersection with item response theory, things of that nature. So there's a trade-off. An inch wide, or an inch deep and a mile wide, or a mile deep and an inch wide, I don't know. So there's tough choices. Yeah. I feel your pain.
I mean, as long as it's fine and you think that it's normal, it's fine.
I would say I think it's definitely normal. I think most people are more frustrated at the end of some of the things that they learn than satisfied, because you realize, we've talked about this before, there's the rate at which your awareness grows about what you don't know vastly exceeds how much you learn. So as soon as you learn one thing, you realize that there's 10 other things that you didn't learn, and that's really painful at times. And you're not alone. I feel the same way. The more you do research, the more you realize you don't know, which is really somewhat defeating, but hopefully motivating eventually.
Ben, can I ask a practical question? So if you were writing up these results for a paper, what exactly, and I think that's what I struggle with IRT, is there's so many parameters, there's so much output. Like, what is the focus of what are you reporting, I guess?
So it depends on what your journal is and what your purpose is.
Okay.
If you're writing up, in a measurement journal, and your principal focus is psychometric properties of a particular scale, then you would report a lot of statistics.
Okay.
Typically, if you're talking about a more substantive journal, like the types that we've talked about earlier, not much of any of this would probably make it into the paper.
Okay.
People are not particularly interested in or they don't understand the psychometric models, and so sometimes you refer them to a technical report, or sometimes you outline the brief characteristics.
Mm-hmm.
I don't think that, I don't know what to say. That's, in some ways, it's not such a good idea, but in other ways, there's only a certain amount of space. So different journals focus on different things.
Right.
It depends on what your focus is.
Yeah, I guess I think for SEM, it's pretty clear what the reporting conventions are across journals. It's like you report this, you report loadings, you report model, and then an IRT, it's like completely different.
Yeah, that's true, but in some ways those fields are starting to intersect, and so you can start to report some of those things. We've talked about different fit statistics, global fit statistics, which can be kind of useful in describing. In structural equation modeling, they would typically report things like the fit statistics, the global model fit statistics, and depending on the journal, the loading patterns or the kind of magnitudes of the coefficients. So I don't know how much space you have, or what diagram. I mean, I think as a rule of thumb, or a guideline at least, it'd be very useful to consider what people write up in SEM and use that as a guidepost for what you should probably be doing in IRT. Okay. In the end, I mean, IRT is subsumed by SEM, so to speak. It's part of SEM. Now, to some extent, that's not. Technically, I think it is completely true, but to some extent, it hasn't been true, at least historically, because SEM grew up out of kind of a covariance analysis.
Right.
And so that explicitly deals with variables that are continuous indicators. And so that excludes, everything's been developed for continuous variables, or under the assumption that at least they're well approximated by that. So, but more formally, I mean, there's no reason why SEM has to be specifically devoted to variables that are continuous. There's categorical, there's no reason why that. And so I think that's probably the case in the state of the field right now. So in some ways, IRT, or you're just doing an SEM analysis that just happens to be principally focused on the measurement models, and you're dealing with categorical data. But you can follow similar guidelines, although some of the statistics don't always transfer very well. So. Okay, question 2. Said use random person effects and random item effects. So if we look at the second model here, it just treats the items as random, which is this code right here, and then persons as random. And that way, there's 2 types of latent variables now. There's an item side latent variable, difficulties, and there's a person side latent variable, the propensities to, I think, the management's communicating well. If we ask for a summary of that model, we'll see that the variance for the persons is about the same that it was a minute ago. It was 0.56 a minute ago, now it's about 0.55. And now in addition, we get the variance of the variables, or the variance of the item difficulties across items. So in that case, it's about 0.5. If we wanted to get the specific estimates of the difficulties or the easiness parameters, we could ask for a summary of them, or posterior modes of their distribution. We can get some answers of that nature. We can compare those back to these are considered the random effect estimates of item difficulties. In other words, we're treating these items as if we're treating them as a random effect now, as opposed to a fixed effect, where the random effect kind of envisions that these items come from a larger pool of items, and we've sampled just a small portion of a larger population of items that we might consider. In contrast with fixed effects, you're specifically focused on those items. You're interested in drawing inferences to, in this case, people, with those items fixed. Those specific items, not using different items. So it just depends on the differences in your target of inference. As sample size increases, another sample size meaning the number of items and the number of people, those 2 answers, fixed and random effects versions, will converge quite quickly, somewhere around, 20 or so. And then the last question said, using these data, create a new item covariate that assigns the last 2 items to a value of 1 and the item covariate value of the remaining items to a 0. And estimate a Rashmanoff, trying to explain why some of these items differ in terms of their easiness. So if we want to go ahead and estimate that, just develop this little item covariate matrix. I forget.
You just had to sort it.
Yeah, which I had to sort it before I did this?
Yeah, you sorted it first.
Good.
You had it as numeric. So order parens as numeric, as dot numeric. Yeah. Yeah.
That look great?
Yep.
So we have first variance is more or less the same, about 0.55. The reason why is we haven't, so what we're doing here is a type of an explanatory item response model, or another way to say that is a structural equation model. In a structural equation model, you have measurement models or submodels for each measurement, each latent characteristic, and then you have structural relationships or regression arrows between those latent constructs. And when you have those regression arrows, you explain some of the variation in the latent construct. So in IRT, people often have called this explanatory item response models. So we're trying to explain some of the variation. Right now, we haven't included any covariates that would explain why people differ. However, we did add a variable as to why the difficulties or easinesses of items differ across items. So before we had the variance in terms of the easiness parameters across items was about 0.5. Now it's been reduced down to 0.39, or about 0.4. So we're explaining about a fifth of the variation. In other words, 20% of the variation that explains why items differ, 20% of that owes to the differences between these 5 items or 6 items that we just used, and I forget, they were called union items, I think, right?
The last two.
The last two.
The last two.
Union-related items. So, 20% of the variance in item difficulties is attributable to the kind of union-focused nature of the questions. So that might be a useful hypothesis or a useful information if you're trying to design items and try to understand how they're functioning. If we wanted to draw inferences on this, we would, one way to do it is a wall test or a likelihood ratio test. We could do that as well. For the moment, we see that there's not really typical evidence of 0.05 or less. So we might fail to reject the null hypothesis that the union-related items are different than the other ones. But with a larger sample size, you may find a significant relationship. So going back to our questions, report the coefficient associated with the item covariate. In this case, it's 0.66. So a 1 unit change in the item covariate, in this case going from a non-union referenced item to a union referenced item, is associated with a 0.66 unit change in the log odds of answering that item correctly. Does the item covariate have a statistically significant association? No. Returning to the original question on slide 5, what is it about these? So if we just take a quick look at these items, those last 2 items, which is the ones that we're focusing on, have the words union in them, or more technically, they describe interactions and communications that are formalized through the union. And so that perhaps is an indicator of a high level of communication or a very formalized communication in an institution or a corporation. So that may be influencing people's responses. Any questions on the homework?
Can I say for question 1, why the output for R does not show the item difficulty for item 1?
So are you talking about the question or the code?
The
Or both? Code.
Both.
Oh, all right. Which one? So you're talking about question 3A?
Question 1.
Question 1, going back to this one?
Yeah. Then the output does not show the item difficulties for item 1.
I think it does. If we look at the summary, the item difficulty for item 1 is this right here?
This is for question 2. Would you please?
No, this is question 1.
That's one.
Oh, it's for question 1.
I think she needs the output before you put in -1.
Oh, so the
Yes.
other, like, so this, the item difficulty is right here.
Yeah, here. So it is for.
That is item 1.
Oh.
It leaves, so if you look at it, the difficulty here is 0.58, and then when I did it a minute ago, when it said item 1, it's 0.58. It gives you the same answer.
Oh.
So the reason why is that R has to choose a reference category, and it chooses the lowest level of the categorical variable. In this case, it's level 1 or item 1. So it takes item 1, the value for item 1, as to be the intercept. make sense?
So I do not need to make the divisions of the intercept for item 1 and item 2 to obtain the intercept for item 2.
For item 2 you do. So for item, so for item 1, this is the difficulty or the easiness, 0.58. For item 2, it's just the sum of these. So it would be something like 0.5.
Oh,
And then for item 3, it's the intercept plus 0.4 or plus negative 0.46. So there's no difference. I know we're dealing with items, but there's no difference between this and using dummy coding. So whenever you use dummy coding, if you want to say if one category represents males and one category represents females, if you code males as 1, then implicitly females are coded as 0. So when you get your model or regression model, the intercept will be focused on females, and then the indicator is the increment associated or decrement associated with males. And so in order to get the male, you have to have the females plus the male indicator. Does that make sense?
Yes.
There was one line of output up there about something about the residuals. Can you just explain what that was? If you go up,
Tell me when to stop.
there, scaled residuals. Can you explain what those are?
So that's just describing the distribution of the residuals. In
Okay.
other words, the discrepancy between your predictions, the observed and the predicted.
Okay.
That's it. So they're just giving you, what's the minimum, what's the maximum.
I got you.
Other questions? All right. Well, without further ado, I think Seenum's up.
Oh no.
Oh, yes, come on.
I cannot take it.